some notes about the Doppler effect. So this is the apparent shift in frequency observed from source frequency due to the relative motion of the source to the medium of transport or the observer to the medium of transport. Okay, a couple of things about that definition that I want to really highlight. Apparent shift. A lot of people read that and think, but Vaughn, the frequency is shifting for the observer. Right, but what I'm saying apparent is because the observer is assuming that the source is changing the frequency because we have this thing in our head that source is the only thing that determines the frequency. I never said that the motion of the source couldn't also help determine the frequency. So there we go on that. So the apparent shift is because the source isn't actually changing the rate at which it puts out waves. So that's apparent. The second thing that I really want to highlight here is the motion that we care about is not the motion of the source relative to the observer or the motion of the observer relative to the source. It's how both the source and the observer are moving relative to the medium of transport, right? Really, all that matters with the Doppler effect is how the source and the observer are moving compared to the waves, because that's what the medium of transport is going to determine how the waves move through it. So the basics of what we saw here. Let's say that I am tapping. I have a source and I'm tapping here, right? We would, if we took a snapshot in time a little bit later, we would see waves traveling outwards from our source. These should be concentric circles, even though I didn't quite draw them there, but these wavelengths should be uniform in all direction as the wave energy travels outwards. I can draw some rays to represent the wave energy traveling outwards. There you go, right? And that's what a wave pattern normally looks like. So let's first look at moving source to see what causes the Doppler effect. So the moving source, notice here, I had concentric circles because here my source was tapping in exactly the same spot. But now our source isn't going to tap in exactly the same spot. The source is going to move along. And so each of my circles is going to be centered on a different spot. So if this circle, boom, this is the latest one, the next circle would have been centered here, right? But would have had time as it moved, as the source moved from here to here to expand. And so I'm just going to draw a circle that's supposed to be centered on that dot. It didn't quite work there, right? Centered on that dot. Now, the previous circle would have been centered on this dot. It'd probably work better if I had a compass, but there you go. Now we have a circle that's centered on this dot. This picture is not perfect, but there you go, and so on and so forth. The important thing here to see is that, and I'll draw a better picture when I'm not trying to actually show what's going on here, that in front of the source, the wavelengths have gotten smaller, and behind the source, the wavelengths have gotten larger. Now, what this picture doesn't show very well, which is a true statement, is that the wavelengths in front of the source are uniform. It's not that if you go further from the source, they get smaller and smaller. No, they are less than what they were. Same thing here, it's that these wavelengths should be equal and they are greater than what they were. So what hopefully we should have seen with a moving source is a shift upwards in wavelength behind the source from what it should have been, and a shift downwards in wavelength in front of the source. Therefore, if it's a shift upwards in wavelength, that an observer behind the source should hear or should experience a smaller frequency than what the source emits, 1t. And here we should experience a higher frequency than what the source emits in front of the source. And as I said in the other video, I'm not going to look at to the sides because that geometry is a little bit more complicated. So therefore, just to bring that together, if the source moves toward the observer, the frequency observed is going to be higher than the frequency of the source. Now, a note on grammar there. I'll write it out. The frequency observed is higher than the frequency of the source. Notice I did not say the frequency observed is getting higher than the frequency of the source. No, it is a finite shift upwards from the source frequency. Similarly, the source, if the source moves away from the observer, the frequency that is observed is going to be less than the frequency of the source. Once again, the frequency observed is less, not as getting smaller than the frequency of the source. So if I were to graph that, right, let's say that this is the frequency observed, and here is something like location, and here is where my observer is, okay? And the source is going to move towards the observer, then move away from the observer. If this was the frequency of the source, as the source moves toward the observer hears a higher frequency than what the source is emitting. It is a constant shift higher as well, right? That delta F there is a constant. Then passes the source. So if we want to be really formal about this, it is a piecewise function. Now, the observer hears something or experiences something that is lower than what the source is putting out, right? Notice it is a constant shift, right? If I call this change in frequency before, change in frequency after, those two are not the same as well. The math of the Doppler effect will prove that to us a little bit later. But it is a shift up or a shift down. It's not getting to be a higher frequency or getting to be a lower frequency. It is a higher frequency or it is a lower frequency. And that is a really important distinction for the Doppler effect as well. And we'll talk about the degree of shift. Now, one thing that we saw here is that the greater the source speed, the greater the shift, right? Both of these delta Fs would be larger if the source was moving quicker, okay? The other thing we saw with the source moving was when the source was moving faster than the wave was. That's when we got our overlapping waves like that, where we have this construct of interference there. That's something that's called a bow wave, like the bow of a boat, right? Because it looks like the wake of a boat, when the velocity of the source is exactly equal, that's when you get the best sort of overlap there. And oftentimes that bow wave is called a sonic boom. Okay. Now, moving observer. All the notes are pretty much identical, but the reason why the Doppler effect is happening is different. Here we have the very uniform wave pattern, so it's not a distortion in the wave pattern. Remember what we said? If the observer, there's my observer, was moving closer, not only would they pick up the waves put out by the source,